Welcome back, folks. This is Mr. Johnson with you once again. This is lecture 1.4 out of our AP Chem 2 book. I'm on page 44 of the ebook, and this is determining rate laws from experimental data. First thing I'm going to do is take you to the whiteboard, review the key concepts from the last 3 College Board lectures you just watched, and then we'll get into this. The first thing you learned about was how reaction rates are measured, and they are measured through the rate of disappearance of either a reactant or reactants or product or products. Notice this graph depicts this, that over time, reactant concentration goes down, product concentration goes up. The rate of the disappearance of a reactant, or the rate of appearance of a product, is greatest at the beginning of a reaction, because that's when the concentration of reactants is highest, and therefore the reaction rate will be greatest. Reaction rates are greater when concentration of reactants are higher. Because reaction rates, by convention, are always positive, if it's the change in the concentration of a reactant that is being measured over time, we want to have a negative sign in front of the change of the concentration of the reactant, because the reactant concentration will be going down, and that negative causes the reaction rate to overall be positive. If it's a product whose concentration is being measured over time, there will always be an increase in that, and therefore the reaction rate will already be positive. Notice that because C is being produced at twice the rate B is, there's a 2 in front of C and a 1 in front of B, we see C appearing at twice the rate that we see B appearing, which is the green line versus the red line. Although the most common way to measure and publish a reaction rate is the change in concentration of a reactant or a product over time, it really can be the change in any measurable quantity of a reactant or a product over time. So it could be the change in the mass of a reactant as it decomposes over time, or the change in the volume of a product. For example, the volume of gas produced over time could be measured. Most of our reaction rates, though, as we see in the rest of these lectures, will be the change in concentration over time, despite that they can be other units as well. The second lecture you watched was on factors that affect reaction rates. This slide suggests there's 4 factors. I'll throw in a 5th. The reactant concentrations, as we've already talked about, affects reaction rates. The greater the concentration of the reactants, the more frequently they will collide, the faster the reaction rate. Temperature has a huge impact on reaction rate. Besides catalyst, it's the most influential factor. Increasing the temperature of the reactants makes those particles move faster, and by moving faster, they collide more frequently and more forcefully. And it's the more forceful collisions that has the biggest impact on raising reaction rate. Surface area can affect reaction rates if one of the reactants is a solid. If a solid is put into smaller pieces, has greater surface area, there's just more places for the reaction to occur. It's kind of like raising the concentration, but it's different, and the reaction rate will go up. And then if you add a catalyst, a substance, and we'll talk more about this later, that is not altered, but that brings the reactants together or brings them together with a better geometry, that can dramatically affect reaction rate. In fact, catalysts can up reaction rates by hundreds or thousands or sometimes millions of fold. The final factor is the state of matter that the reactants are in. Liquids will react faster than solids. Solutions typically react faster than liquids, and then gases, where the particles are free to move, react the fastest. So the nature of the reactant, or the state of the matter reactant, also affects reaction rates as well. And then the final lecture was on collision model or collision theory, which talks about the fact that for a reaction to occur, if there are 2 or more reactant particles, they first and foremost have to collide. The reactant particles must collide. In addition, they have to collide with the proper orientation. They have to hit each other at the right way so that the right atoms can break away and the other atoms that need to bond can bond. And there's a model in the video for how that works. As well, the reactant particles need to collide with enough force or with sufficient kinetic energy to overcome activation energy. There's a minimum amount of kinetic energy that reactant particles must collide with for that collision to be successful. And that's the third key feature of collision theory, which is that reactant particles, again, must collide with the minimum kinetic energy or with energy that is equal to or greater than activation energy. And finally, I'd like to acknowledge that in one or more of those lectures, they brought up a reaction order or an order of a reactant. That may not have made sense. That's what this lecture is all about, is figuring that out and learning what those terms mean. First thing I'd like to do is to introduce you to the general format for a rate law. A rate law is an expression or an equation that describes the relationship between the rate of a reaction and the initial concentration of one or more of the reactants, along with a constant, a rate law constant, that establishes the relationship between the left-hand side of the expression, the rate, and the concentration of the reactants. Again, initial concentration. So on the left-hand side, we see the word rate. That will be in molarity per second. It says molarity per time, but time is almost always measured in problems in seconds. So the rate will be in molarity per second. These brackets, remember, represent concentrations. So these brackets represent the concentration of reactant A initially, at the very moment the reaction starts, and then B will be the concentration of reactant B as well initially. M and N represent their orders. They are exponents. They can be a 1, a 2, and every once in a while we might see them as a 3. What those orders are establishing is the effect that the concentration has on rate. If M is a 1, if the order for reactant A is first order, then that means that if the concentration of A doubles, the rate doubles. There's a linear relationship between the concentration of A and rate. But if M were a 2, if it were second order with respect to A, then that means there's an exponential relationship between the concentration of A and rate. And if the concentration of A were to double, for example, and again M were 2, 2 squared is 4, we'd see the rate quadruple. In some cases, and we'll learn why later, raising the concentration of reactant doesn't just have a linear effect on rate, it has an exponential effect. The sum of the orders, the sum of M and N in a rate law, for example, is called the overall order. And from time to time, you might be asked to first figure out what the order is for each reactant and then what the overall order is. And that's, again, what this lecture is primarily about. Finally, K is the rate constant that allows the two sides of these expressions to be equal to each other. We'll talk about how K can be derived and what its units will be. One thing I'll share with you, which this slide also says, is that K is dependent upon the specific reaction and it's dependent upon the temperature at which that reaction occurs. So let's say our reaction is fixed. The only thing then that can alter K is the temperature. What temperature raises is K, and by K raising, the rate goes up. What is the only factor that can change K? Once we're looking at a fixed reaction, the answer is temperature. Temperature raises the rate law constant. All right, we're back to our book. Again, we're on page 44, and I encourage you to do this warm-up on your own, which will get your head around the concepts that you're going to see me talking about in the rest of this lecture. So take a peek at this warm-up, do it on your own, come back when you're done. See you in a bit. For 1, I found that the number of circles went from 4 to 8 from system 1 to system 2. That's a 2-fold increase. 8 divided by 4 is 2. Meanwhile, the reaction rate from system 1 to system 2 went from 0.01 to 0.02, which is also a doubling. They both went up by a factor of 2. From systems 1 to 3, the number of squares went up from 4 to 8. That's a 2-fold increase. And the reaction rate went from 0.02 to 0.04, which is also a 2-fold increase. When the change in concentration is the change in rate, 2x equaling 2x, and 2x equaling 2x, that means that they're first order, that the relationship between concentration and rate is linear. When the rate goes up by the same factor that the concentration goes up, then the order is first order, and we say that the order for reactant A is 1. The same will be true for B, because its concentration was doubled from system 2 to 3. So did the rate double, and when the rate and concentration go up by the same factor, it's linear, it's first order, so we'd say it's first order with respect to B. If we were asked what the overall order of this reaction is, we'd say it's 2, because the sum of the orders of the individual reactants, 1 and 1, is the overall order, which again is 2. What the rest of this lecture will be about is doing this same thing, but not from a particle diagram perspective, but from numbers that are slightly trickier to deal with, and figuring out how we can determine the value and unit for K. That's what the rest of this lecture will be about. And before we solve another problem, I want to stress once again something I said a moment ago. What we're looking at are initial rates of reactions, how the initial concentration of one or more reactants affects the initial rate of the reaction, which, as we know, is going to be the highest it will ever be, because that's when the reactant concentration is greatest. Again, this is all about determining the initial rate of a reaction by looking at the effect that the concentration of reactants has on that initial rate. This is actually a problem out of our book, but I've jumped to the whiteboard where I can, of course, write a bit better. And what we're looking at here is a table. This is a characteristic looking table that will allow us to determine the rate law given these runs. The first thing we want to do is write the general rate law. General rate law always starts with the word rate. So we're going to write rate, then an equal sign, and then K. At some point, we may put a value in for K, but for now it's just a K. And then we put each of the reactants in brackets. And in this table, it looks like the reactants are bromate, BrO3 minus, bromide, Br minus, and then H plus. So there is the general rate law. What we need to figure out is what the orders are with respect to these reactants, what the order is for bromate, for bromide, and for hydrogen. All right, here's how to think about this, and it's a great little puzzle. The first thing we're going to do is figure out what the order is with respect to bromate, BrO3 here. What we do is look for two of the 4 runs, where the concentration of bromate is changing, but the concentration of bromide and hydrogen isn't. So we can just evaluate the effect of the change in concentration of bromate on the initial rate. So take a moment and look for which 2 runs have the concentration of bromide and hydrogen fixed and the concentration of bromate changing. Looks like runs 1 and 2 fulfill that criteria. The bromide is not changing, the hydrogen's not changing, and the bromate is. So we're focusing on runs 1 and 2 to determine the order for bromate. All right, so the first thing we ask ourselves is what's happening to the concentration for bromate between runs 1 and 2, between the lesser concentration and the greater? Well, from point 1 to point 2 is a doubling. There's a 2-fold increase in the concentration of bromate. We then go over and look at the initial rate and see what the change in the initial rate is. And going from 0.008 to 0.0016 is a 2-fold increase as well. 0.0016 divided by 0.0008 is 2. When the change in the concentration is the change in the rate, that's a linear relationship. It's first order. So the order with respect to bromate is first order. We can put a 1 in there. All right. We will now do the same thing for bromide and hydrogen that we did for bromate. We want to look for 2 runs where the concentration of bromide doesn't change. Where the concentration of bromide changes, but hydrogen and bromate doesn't. So let's do that one now. See if you can figure out which 2 runs to use for bromide, where bromide's concentration is changing, but hydrogen and bromate is not. Looks like runs 2 and 3 fulfill that criteria. Bromide is going from 0.1 to 0.2, whereas hydrogen stays at 0.1 in both runs, and bromate stays at 0.2. So I ask myself, by what factor is the bromide concentration increasing? 0.1 to 0.2 is again a 2-fold increase, and going from 0.0016 to 0.0032 is also a 2-fold increase. Again, when the change in concentration is the same as the change in rate, it's a first-order reactant. Had bromide tripled and the rate tripled, that would also be first order. Or had bromide quadrupled and the rate quadrupled. Or had bromide halved and the rate halved. Those are all examples of linear relationships or first-order reactants. So I'm going to pop a 1 in here for bromide. All right, so now let's find the runs that fulfill that criteria for hydrogen. We're looking for runs where the concentration of hydrogen does change, but bromate and bromide don't change. All right, looks like runs 1 and 4 will fulfill that criteria. Hydrogen concentration is going from 0.1 to 0.2. That's a 2-fold increase. Bromide, meanwhile, and bromate are staying fixed at 0.1 in both cases. So then we go for the rate change between runs 1 and 4. 0.0008 compared to 0.0032 is a 4-fold increase. 0.0032 divided by 0.0008 is 4x. Here's a case where the change in concentration is not the same as the change in rate. So what we want to say to ourselves is 2 to what power is 4? 2, because the concentration is doubling, the rate is quadrupling. 2 to what power equals 4? Well, the answer to that is 2 squared. 2 squared. The order with respect to hydrogen is 2. It's a second-order reactant. Had the concentration doubled, which it did, and the rate gone up by a factor of 8, then we'd say, well, 2 to what power is 8? That's 3. 2 to the third is 8. That would be a third-order reactant. So be aware you might see a third-order reactant, although it's a little bit less common. So we have just determined the order of each of the reactants. It's 1, 1, and 2. And the overall order, if we were asked for this, would be 4th. It's a 4th overall order reaction. The next thing we'll do is another sample problem like this, and then we'll learn how to calculate K and how to figure out what the units for K are, and that will wrap up this lecture for today. All right, so we've got another problem like the last one. There's 4 sets of data. We've got 3 reactants here, the manganate ion, oxalic acid, and the hydrogen ion. Try to figure out what the order is for each of these reactants by picking the right sets of data. Come on back and see how you do. For the manganate ion, I picked experiments 1 and 2 because its concentration is changing there, whereas the other ones are not. And if the concentration is doubling and the rate is quadrupling, 2 to what power is 4, it is second order with respect to manganate. For the oxalic acid, I picked experiments 2 and 3 because, again, its concentration is changing there, the other 2 are not. Its concentration is doubling from experiment 2 to 3. The rate is also doubling. It doesn't maybe look like it initially, but 1.6 times 10 to the minus 3 over 8 times 10 to the minus 4 is in fact 2. And when the concentration and rates do the same thing, that's first order. So first order with respect to oxalic acid. But then for hydrogen, we're seeing that in experiment 3 compared to 4, the concentration is doubling. Of course, the other reactants are staying the same. That's why we picked those. Yet the rate is not changing. When a reactant concentration changes and the rate doesn't, that means that reactant has no effect on the overall rate. 2 to what power is 1? Well, the answer is 0. It's a 0-order reactant, which we haven't seen before, which is telling us that although hydrogen is a reactant, it's having no effect on the overall rate. And we'll learn why later, why a reactant wouldn't have an effect on the overall rate. When we rewrite this rate law, we will omit hydrogen ion from the rate law altogether because hydrogen to the 0 power is 1 and it will disappear. And then there's our overall rate law with hydrogen being omitted, and the overall order is 3, or it's third order overall because the sum of the exponents is 3. The next and final thing we will do is learn how to calculate what the value for K will be in a case like this and what its unit will be. So we're going to use the rate law we just derived for this set of data, and in so doing, solve for K. All we need to do is pick one of the 4 sets of data, we could use any 4, and plug in the rate that's given to us and the concentrations for each of the reactants that are given to us into this rate law. And that'll give us the proportionality constant, K. So let's plug in the values for the rate, for the manganate ion, and for the oxalic acid from experiment 1, or from the first row. But again, we could do it for any of the data sets, knowing they all establish the same relationship. So I plugged in the rate from the first row. I plugged in the manganate ions concentration from the first row, and I've squared it because that's what the rate law says I must do. And I've plugged in oxalic acid's concentration. And I've included the units. The unit for rate is molarity per second, and molarity is moles per liter, so you could also have written moles per liter per second, but it's easier, arguably, to write molarity per second. And the 2 concentrations, of course, have the units of molarity. So we'll solve for K and see what unit we get. To isolate K, I've divided both sides by 1.0 times 10 to the 3 molarity squared and 1.0 times 10 to the 3 molarity, which, because those values are the same, is 1.0 times 10 to the minus 3 molarity cubed. And the value we get is 0.2, but the unit, which is a little bit tricky, is going to have at first molarity in the numerator and seconds in the denominator, but we're also dividing by molarity cubed. So we've got molarity over seconds times molarity cubed. But if we cancel one of these molarities, we ultimately get for the unit 1 over seconds times molarity squared. The final value for K is 0.2, and its unit is 1 over seconds times molarity squared. There will always be a unit for time in the denominator for a rate constant. There will always be seconds. The question is, what will the exponent on molarity be? And the final segment of this video is for you to know what the pattern is for the unit for K so that you don't have to derive it every time. Again, K's unit will always have seconds in the denominator. The question is, what will the exponent be for molarity? So we're back in our book. We're on page 46 of the ebook looking at the section titled Determining the Rate Constant. And here we see in table 142 the pattern that exists for the rate law constant unit compared to the overall order of the reaction, which again is the sum of the orders of each reactant. If a reaction is overall 0 order, which is unlikely, the unit for the rate law constant will be molarity per second, which could also be thought of as 1 over seconds times molarity to the minus 1. We could bring molarity from the numerator to the denominator and give it an exponent of minus 1. 0 order, molarity is to the minus 1. If it's first order, it's just 1 over seconds. There is no molarity. Or we could argue it's molarity to the 0. First order is molarity to the 0, whereas 0 order was molarity to the minus 1. If it's second order, it's molarity to the power of 1 in the denominator. Second order, molarity to the 1. If it were third order, by the way, it would be 1 over molarity squared times second. And if it's nth order, whatever that overall order is, it is 1 over molarity to the n minus 1 over seconds. What that's telling us is that the exponent for molarity in the denominator is always 1 less than the overall order. And that's based on the derivation we just did. You could see how that works. Again, the exponent for molarity in the denominator of a rate law constant unit is always 1 less than the overall order. The overall order is second order. It's molarity to the 1 in the denominator. If the overall order is first, it's molarity to the 0 in the denominator, or it doesn't exist. So hopefully that pattern is making sense to you. That's arguably the easiest way to figure out what the rate law constant unit will be as opposed to deriving it. But you can always hang on to the units when you're deriving k and determine what the unit will be through the math or algebra you do. If you feel like you've gotten this, you can sign off. And if you'd like to do one more practice problem with me, determining the value and unit for k, I'll do one more with you. If this is goodbye, folks, have a great day. And if not, I'll see you in the next clip. We're looking back at the first rate law problem we did together a bit ago. Here is the overall rate law that we derived together. I recommend you try to find the value for k and its unit on your own, and then come back and compare your work to mine. And when I divided both sides by 0.1 to the 4th, I got k equals 1 over seconds times molarity cubed. Seconds, remember, always remains in the denominator. And if we've got molarity on the left divided by molarity to the 4th on the right, we get molarity to the 3rd in the denominator. Again, we're seeing the pattern. The overall order is 4th order. 1 plus 1 plus 2 is 4, which is why the exponent for molarity is 1 less than that in the denominator. It's molarity cubed because it's overall a 4th order. And one thing I didn't mention a bit ago is you might be asked to then publish the overall rate law with the value for k in it. So let's do that as one last thing. Plug this k into our overall rate law and see what it looks like. And there she is. The rate is equal to 8, 1 over seconds times molarity cubed times bromate to the 1, bromide to the 1, and hydrogen ion to the 2. Something that's somewhat commonly done is expressing this rate law constant unit with no denominator. And I've written that as an alternative below so that if you see it, you're comfortable with it. You don't have to do this, but instead of saying 8, 1 over seconds times molarity cubed, you could say 8 seconds to the minus 1, molarity to the minus 3, which of course brings those up to the numerator, but gives them a negative exponent as a result. So while you don't have to do this, this is something you might see in future problems. That's it, folks. Thanks for hanging in there. Been great to be with you today. Have a great day, whatever it is you're about to do. Mr. Johnson signing off.